Hello everyone, and welcome back to some more remote learning. In today's video, we're going to be learning about how to evaluate simple limits simply by plugging in a. So the first thing we're going to talk about is limits of linear functions. Now, if you think about a linear equation, is there any restrictions on the domain of what we can plug in for x? Is there any x value that will give us something that's undefined within those real numbers? And no, there isn't. So because there's nothing that will give us undefined, when we have a linear function, we're going to simply plug in the value that x is approaching into that equation to see what the function approaches. So we'll say that the limit of f of x as x approaches a, if f of x is this equation, mx plus b, that's that slope-intercept form of the equation, well then, we're simply plugging in a for x. So that's going to be equal to m a plus b. Whatever number we get when we plug in a, that's what our limit is equivalent to, which this ma plus b is f of a. If we were to take a and plug it in for x, we would get ma plus b. So quickly, looking at this graph on the right, I have some function, and I believe it's y equals 1/2 x that I have graphed. And if we're approaching 4 in the x, if I want to find the limit of f of x as x approaches 4, well then, I know my function is 1/2 x, so I'm looking at the limit as x approaches 4 of 1/2 x. All I'll do is plug in 4 for that x. So we get 1/2 times 4, which gives us 2. And you can indeed see that that limit as x approaches 4 is 2. And that's it. That's how to do a limit of a linear function. We're just plugging in that a value right on in for x. So I have a couple examples below where we will work with taking the limits of linear functions. So if we're going to evaluate the limit of 2x plus 1 as x approaches 0, this is indeed a linear in the form of mx plus b. And if we're taking the limit as x approaches 0 of that function, we're going to plug 0 right on in. So we'll do 2 times 0 plus 1. 2 times 0 is 0 plus 1. Our solution in a is 1. If we move on to b, we have the limit of x plus 3 over 4. This is indeed a linear function still because I can split up my fraction into x over 4 plus 3 over 4. So you can see that my slope is 1/4 and I have a y-intercept of 3/4. Since it's linear, what am I going to do? I'm going to plug 5, that a value, right on in for x. So I'll get 5 plus 3 over 4, which is 8 over 4, which equals 2. So the limit of this function as x approaches 5 is 2. The function itself approaches a value of 2. Moving on to c, we're taking the limit of 45x as x approaches -3. What do? Plug -3 right on in for x. So this is going to equal 45 times -3. And 45 times -3 is going to give us -135. So the limit of this function as x approaches -3 is -135. And now on to d, again another linear equation, 4x plus 9. We're taking the limit of that function as x approaches 3/4. So I'll take 3/4 and plug it on in for x. So 4 times 3/4 plus 9. You can see that my 4's will cancel out to leave me with 3 plus 9, which is 12. So 12 is my solution in part D of example 1. Now we'll move on to taking limits of polynomial functions, where polynomial functions are some coefficient times x to an integer n, to some positive integer n. So you can see here I kind of wrote out a basic definition. We have some coefficient, a sub n, and there's x raised to the n. The next coefficient, a sub n minus 1, x raised to the n minus 1. we have some other coefficient with x squared, some other coefficient with x to the first, and then some other coefficient essentially with x to the 0 because x to the 0 is 1. And of course within those ellipses we have all the values in between in -1 and 2 that I just don't have pictured. So if we're taking the limit of a polynomial function, the limit of p of x as x approaches a, so the limit of our polynomial function as x approaches a is going to be equal to what? That's going to be p of a. We're going to plug a right on in for x in our polynomial function to see what that limit's equivalent to. And lots of times in the back of my mind, when I'm taking these limits, I like to think about when I'm plugging in values for x, I can always plug those values in as long as my function is not undefined. And for a polynomial, we can plug in any value of x within those real numbers and get a solution. And that's the same with those linear functions as well. So all I'm going to do is plug in a to figure out the limit of my function. So you can see here, like if we were to approach, let's say -1, coming from the left and coming from the right are going to be the same thing, so that limit will indeed exist, and it happens to be whatever value I get when I plug in a for my function. So let's go ahead and evaluate these following limits. So if I'm taking the limit of 5x to the 4th minus 3x cubed minus 6x squared plus 2x minus 1 as x approaches 0, what am I plugging in for x? I'm plugging in 0. So if I plug in 0, all of these terms containing x, when I plug in 0 for x, go away. So I'm left with just a -1. So my limit is -1. For b, I have the limit of x cubed plus 7 as x approaches -2. I have a polynomial. I'm just going to plug -2 in for x. So this is going to give me -2 cubed plus 7, and negative cubed remains a negative, and 2 cubed is 8. So this is going to be -8 plus 7, which also gives me a -1. Moving on to part C, my polynomial function in this case is x squared plus 3/2 x, and I'm plugging in 1/2 for x. So I'll get 1/2 that quantity squared plus 3/2 times 1/2. 1/2 squared is going to give me 1/4, and I'll be adding that to 3/2 times 1/2 is 3/4. 1/4 plus 3/4, 4/4, that's going to be equal to 1. And lastly, D, I have the limit of x to the 99th minus 4x to the 27th plus 5. And I'm finding the limit of that function as x approaches 1. So I'm taking 1 and plugging it in for x. So I'm going to have 1 to the 99th minus 4 times 1 to the 27th, and then I'm adding to that. 1 to the 99th is 1, minus 4 times 1 to the 27th is 4 times 1, which is 4, plus my 5. 1 minus 4 gives me a -3, plus 5 will give me a +2. So that's how we work with limits of polynomial functions. Now let's talk about working with limits of rational functions. Because if we think about a rational function, if p and x and q of x are the polynomials, a rational function is in the form of some polynomial p of x over q of x. That's a rational function. I have one function of x and I'm dividing it by another function of x. So when taking the limit of that, just like up above, I'm going to plug a in for x in both of my functions. So the limit of my rational function, p of x over q of x, as x approaches a, is going to be equivalent to p of a over q of a. Just like with those polynomials and linear functions above, we're plugging in a to those functions. However, I want to note for rational functions, if we're dividing by a function, what can the denominator not equal? If that denominator equals 0, our function is undefined. So we can only plug a in for x as long as this denominator does not equal 0. Or if it does equal 0, we're able to cancel it out. So if we're just plugging in a for x, q of a cannot be equal to 0 unless we do some algebraic manipulation, which we'll talk about in example 4 below. So let's go ahead and evaluate these limits. So we have the limit of x squared plus x minus 6 over x minus 2, and that's as x approaches 0. So I'm plugging 0 in for x. But before I do this, I just want to double check really quickly that I can do that. Is my denominator going to equal 0 if I plug 0 in for x? Let's check. Plugging in 0, I get 0 minus 2, which is a negative 2. So no, we're okay to simply just plug in 0 for x, because if you think about it, the only x value would make this undefined is if x was equal to 2, which it doesn't. So let's go ahead and plug in 0 for x. So we'll get 0 squared plus 0 minus 6 all over 0 minus 2. 0 squared plus 0, 0 minus 6, that's a negative 6, over 0 minus 2, which is a negative 2. Negative 6 over negative 2 is going to give me a positive 3. So 3 is going to be our solution for the limit of our function as x approaches 0 in part A. Moving on to part B, we have to ask ourselves, what can we not plug into our denominator? Is negative 1 okay? Let's double check. If I plugged in negative 1, I'd get negative 1 squared plus 9 times negative 1. Does that equal 0? Negative 1 squared is 1. 1 plus negative 9 doesn't equal 0, so I'm safe to plug in negative 1. So I'll finish plugging it into my numerator. I'll get negative 1 cubed plus 10 times negative 1 squared plus 9 times negative 1. So this is all going to be equal to negative 1 cubed is a negative 1 plus 10 times negative 1 squared is a positive 10 plus 9 times negative 1 is a negative 9. So I'll write this as minus 9 all over negative 1 squared is 1 minus 9 times 1, which is 9. Negative 1 plus 10 is 9. 9 minus 9 is 0. 0 over 1 minus 9 is 0 over negative 8, which equals 0. So 0 is my solution in this example. So if we're going back to the picture up above, you can clearly see that whatever function I have graphed here, as I approach 3 from both the left and the right, I'm going to some defined value. So I can simply just plug 3 in. However, for this function, I can't just plug in 0, because if I was to plug in 0, I would get undefined. But just because I can't plug it in doesn't mean I still can't take the limit, because even though that point doesn't exist, or that point's undefined, the limit still exists. So let's talk about how this happens. How do we get a hole in that function? Well, that happens when our denominator, q of a, equals 0, and we can simplify and still solve. You'll learn in a later example that sometimes there's just no way to simplify down or manipulate this algebraically to solve for the limit. However, if q of a does equal 0, we could potentially have a hole in our function where the limit still exists. And let's talk about how to evaluate that. If q of a does equal 0, we know we cannot divide by 0, so we're going to try to algebraically manipulate the function and simplify. And there's two different methods we're going to use to attempt to solve. One of those is factoring, and then the other is multiplying by the conjugate. So let's go over example 4 and talk about factoring. So it says we're going to evaluate these limits first by factoring. So what I'm going to do is I'm going to write this equivalent limit. It's going to be the limit as x approaches 2 of my factored function. So x squared plus x minus 6, how do we factor that? what multiplies to give us a negative 6 but adds to give us a positive 1. That's going to be 3 and negative 2. So I'm going to have x minus 2 times x plus 3 in my numerator, and in my denominator, I still have that x minus 2. But look what happens. If we simplify this down, because x minus 2 is multiplied by everything in my numerator, I can cancel out x minus 2 in both my numerator and denominator, so I'm left with the limit as x approaches 2 of x plus 3. What's this? Well, it's just a simple linear function, or a polynomial to a first degree. We can just plug 2 right on in. So this will be 2 plus 3, which equals 5. So we were able to take this rational function and simplify it down into a linear or polynomial function. And that was because if we tried to take the limit as x approached 2, if we plugged 2 in, 2 minus 2 equals 0. We cannot have a denominator equal 0, so we simplified by factoring. Let's look at b. For b, we're doing the limit as x approaches negative 9. If I was to plug in a negative 9, for x into my denominator, I'd get 81 plus negative 81. That would indeed equal 0, and we don't want this to equal 0. So we're going to follow our instructions and simplify this limit down. So we're going to have the limit as x approaches negative 9 of, first factoring my numerator, all of these terms have an x in common. So I'll go ahead and pull out an x. If I pull out an x, that would leave me with x squared plus 10x plus 9. So I need to think what multiplies to give me 9 and adds to give me 10. That's positive 9 and a positive 1. So I'll have x plus 9 times x plus 1. If you want to double check and expand that all out, you will indeed get x cubed plus 10x squared plus 9x. Now for my denominator, again, I have that x in common, so I'll go ahead and pull that x out, and that will leave me with x plus 9. So even if I was to factor it first, it might be easier to see. If I plugged in negative 9 right now, negative 9 plus 9 is going to give me a 0 in my denominator that's multiplied by everything else. So I'm not able to plug that in. However, because I have an x plus 9 multiplied by everything in my numerator, I can cancel it out with the x plus 9 in my denominator. And while I'm at it, let's just go ahead and cancel out these x's as well. Completely simplify this down. It's okay to leave that x in, but if you can simplify, go ahead and do it. So now what I have is the limit as x approaches negative 9 of x plus 1. Now I have a linear function, or a polynomial, so I'll just plug negative 9 in to get negative 9 plus 1, which equals a negative 8. So negative 8 is my solution in part B. So if I was to ask you to take the limit as, let's say, x approached 0 in part B, you would also have to factor and simplify at the start, because if I plug 0 in, I would get 0 in my denominator. And you can see that it factored out nicely and allowed us to cancel it out. Any other number besides 0 or negative 9, however, I can just plug right on in. I don't even need to worry about simplifying it down. And if you notice, this was the same as up above, where I plugged in negative 1. Negative 1 didn't give me 0 in the denominator, so I was safe to plug that in. But 0 or negative 9, my function's undefined, and I have to simplify first. Now I mentioned that there were two ways to potentially simplify down in order to evaluate these limits. The first one was by factoring, and the other one was by multiplying by the conjugate. And I quickly want to note, when you're multiplying that by the conjugate, sometimes it's easier to look at variables to understand why it works. So if I have a plus b, that conjugate is a minus b, or vice versa. A minus b, the conjugate of that is a plus b. I'm just switching that middle sign. When you think about foiling this out, we'll get a squared minus ab plus ab minus b squared. My minus ab cancels out with my positive ab to leave me with a squared minus b squared. So multiplying by the conjugate helps, especially with dealing with square roots, because when we wind up squaring a square root, that square root cancels out, which makes our functions easier to work with. So if you can envision that I had a square root of a plus b times square root of a minus b, that would be the square root of a squared minus b squared, which would leave me with a minus b squared, which is a lot easier to work with than all of these square roots. So let's go ahead and apply the multiplying by conjugate method in order to solve these limits. So looking at number 1, you can see that if I was to plug 4 into my denominator, the square root of 4 is 2. 2 minus 2 would give me 0. So I can't just plug this in. Any other number, as long as it's in the domain, so obviously I don't want to plug in negative x values because I can't take the square root of a negative number, but if I was to plug in something like 3 or 5, those would not give me 0 in the denominator, and it'd be okay to plug them in. However, as x approaches 4, I do indeed get 0 in my denominator. My function's undefined. Let's simplify down by multiplying by the conjugate. So I'll have the limit as x approaches 4 of x minus 4 over the square root of x minus 2, and I'm going to multiply everything by the conjugate so that I'm multiplying by 1. So the conjugate of the square root of x minus 2 is going to be the square root of x plus 2. I need to multiply by 1, so the square root of x plus 2 in my denominator as well. Square root of x plus 2 over square root of x plus 2 is 1, so I'm not changing the value of this, although you can see in my denominator, I'm going to get rid of the square root. So this is going to be equal to, I'm not going to distribute my numerator through because that's not what's giving me an issue with this problem, so I'm going to leave my numerator as is. So I'll have the limit as x approaches 4 of x minus 4 times the square root of x plus 2. Now in my denominator, that's where I'm going to simplify. So if I was to FOIL that out, the square root of x times the square root of x, we know is x. And then we have the square root of x times 2, but we're subtracting 2 times the square root of x, so that goes away. And then we have negative 2 times a positive 2, which gives us a negative 4, so I'll have minus 4. And look what happens. We have x minus 4 in my numerator, multiplied by everything, and an x minus 4 in my denominator that can cancel out. So now I have a simple function that I can go ahead and plug in what x is approaching. So I'm going to plug that a right on into x, which a in this case happens to be 4. So I'll take the limit as x approaches 4 of the square root of x plus 2. Plugging 4 right on in, that's the square root of 4 plus 2, which is 2 plus 2, which gives me 4. So this limit that we first couldn't deal with because we couldn't plug 4 in, we actually got an answer. And in all of these cases where our denominator cancels out, our graph will have a hole. Our function is undefined, but the limit still exists. For part B, we see that square root. If we tried to plug in 1, we'd get 2 minus the square root of 4, which would definitely give us 0. So let's multiply by that conjugate. So we'll take the limit as x approaches 1 of 5 minus 5x all over 2 minus the square root of x plus 3. Multiplying by that conjugate over itself, I'll have 2 plus the square root of x plus 3 all over 2 plus the square root of x plus 3. Simplifying this limit, remember it's not my numerator that's giving me difficulties, it's my denominator. So I'm not going to do all that work to distribute that through unless it's going to help me simplify down later, which I'll decide eventually. For now, I'm going to leave it as is. 5 minus 5x times 2 plus the square root of x plus 3. Now when I multiply by the conjugate, in my denominator, I get 2 times 2, which is 4, and then I'll have a positive 2 times the square root of x plus 3 minus 2 times the square root of x plus 3, so that goes to 0. And then I have a negative square root of x plus 3 times square root of x plus 3, which leaves me with a negative x plus 3. Now in this case, I don't really have a factor that cancels out. And if I plug in 1, I'm still going to get 0 for my denominator. So I think this is going to be the case where I'm going to try to simplify both my numerator and denominator to try to get those factors I can cancel out. So I'm going to have the limit as x approaches 1 of, well, if I was to simplify my denominator down, 4 minus x, and then if I distributed that negative, minus 3, is going to leave me with 1 minus x. Now, does that occur anywhere in my numerator? Actually, it does. What does 5 minus 5x have in common? They both have 5. So if I pulled out 5 from that, I'd be left with 1 minus x, because 5 times 1 minus x is 5 minus 5x, and I still have that 2 plus square root of x plus 3 in my numerator. However, because that factor of 1 minus x is multiplied by everything, I'm able to cancel it on out. So now that I no longer have a denominator, I can plug in whatever values I want for x, with the exception of, let's make a note that we need to remember what kind of values fall into the domain of a square root function. Obviously, we can't have negatives underneath that radical, but plugging in 1 is not going to give us that. So we don't have to worry about that for this problem. So I'll take my limit as x approaches 1 of 5 times 2 plus the square root of x plus 3. Plugging 1 right on in, I'll get 5 times 2 plus the square root of 1 plus 3. That's going to equal 5 times 2 plus the square root of 1 plus 3 is the square root of 4. Square root of 4 is 2. 5 times 2 plus 2 is 5 times 4, which equals 20. So 20 is my solution in part B. Now again, I want to note, when we were dealing with these rational functions, if we got q of a to equal 0 in our denominator, we had to either factor or multiply by the conjugate in order to simplify down and cancel out the denominator, or cancel out that factor in our denominator that made it equal to 0. In some cases, there's going to be no way to simplify down or factor in order to cancel out the 0 from our denominator. But there is a way to still solve for the limit, and I'm going to show you that in a later example video. However, before we jump into that, in the next example video, we're quickly going to go over limit laws so that we get more familiar with taking multiple functions and finding the limit of multiple functions within the same problem. And I'm also going to go over the squeeze theorem, which will come in handy for functions that are hard to simplify. So stay tuned and get ready to eventually learn how to solve for when q of a equals 0 and we can't factor or multiply by the conjugate in order to simplify. But until those next videos, continue to practice and good luck with your online learning.